In the previous video, we saw this maze, but we didn't really answer the most fundamental question. How do you find a path in that maze? In this video, we are going to explore some of the graph traversal algorithms that will help us understand and solve this problem. So hi, I'm Piyush, and in today's video, we are going to explore two of the most crucial graph traversal algorithms that will help us solve this problem. And we are also going to dig deep into understanding how the algorithms differ and what are their use cases. So let's get started. Now at first, let's talk about the most core basic ideas of graph traversals. Now we will be using this particular graph for all our traversal algorithms, and we will now try to explore the inherent properties of a graph traversal. At first, we begin by marking every node in the graph as undiscovered, which essentially means that we haven't visited or encountered them yet. Next, when a node is encountered during traversal, it moves to a discovered state, which means that we have found it, but haven't explored all its neighbors yet. And then we explore all its neighbors and discover its adjacent nodes as well. And once it has been done, or in other words, once it has actually explored all its adjacent edges and nodes, we mark that particular node as processed, meaning that all its neighbors have been discovered as well. So essentially, a particular node moves from an undiscovered to discovered and then finally to a processed state. Now, using this discovered state also helps us prevent revisiting nodes we have already seen, which is especially important in graphs with cycles. Without it, we could have ended up in an infinite loop, continuously exploring the same set of nodes. In practice, during implementation, we typically don't really track all the three states explicitly. Instead, we use a single visited array to mark whether a node has been discovered, and we'll talk more about this later in the video as well. Now, this concept forms the fundamental basis of every graph traversal algorithm. We will now take a look into two of them, and we will start with breadth first search. But before that, there is one important idea that I want you to keep in mind while exploring these algorithms. That is, how do you discover the child nodes? Now, this is really the key, and it underpins every graph traversal technique that we will see. So let's begin with breadth first search, which uses a queue to keep track of the discovered nodes or the child nodes. Let's walk through what the algorithm looks like. It's quite simple. We maintain a queue to hold the nodes that have been discovered, and then for each of the nodes, we remove from the queue, we discover all its adjacent nodes and mark that particular node from the queue as processed. And then we continue the same process for the next node in the queue. So let's simulate this algorithm to see how it works in practice. We represent a graph using an adjacency list, which allows us to efficiently access all the neighboring nodes of any given vertex. Now, we discussed adjacency list in the previous video, and I would recommend checking that out to fully understand this algorithm. Now, at first, we mark the nodes in the graph as undiscovered, and then we initialize a queue with the root node or the starting node of our BFS traversal. And now something interesting happens. We enter a while loop where we keep doing certain operations for each of the elements in the queue. First, we pop out an element and we discover all its adjacent nodes. For example, for node 1, we explore all its adjacent nodes all at once, and we push all these newly discovered nodes into the queue. And after that, we mark node 1 as processed. We then repeat the same process for the other nodes in the queue as well. Next, we pop node 2, and since node 2 has no adjacent undiscovered nodes, we simply mark it as processed. Then we dequeue node 3, and node 3 does have some undiscovered nodes. So we discover them, push them into the queue as well, and now we see that node 1 and node 4 are already discovered. So we can safely mark node 3 as processed as well. And after that, we continue popping and processing the rest of the nodes in the queue, repeating the same logic. Now when node 4 is popped out, it's again marked as processed, and the same goes for node 5. Once that's done, we have completed our BFS traversal, and we have processed all the nodes in the graph. Now, in terms of implementation, we can simplify the process of tracking node states like undiscovered, discovered, and processed using a single visited array. Each index of the visited array corresponds to a particular node, and we will initially set it to false to signify that the node is undiscovered, and it will be then set to true when it's discovered and added to the queue. Since we process a node only after discovering all its neighbors, we don't need a separate marker for processed state. The queue naturally handles that sequencing. This keeps our logic clean and helps avoid revisiting nodes during a traversal with graphs having cycles. Now let's see how we can apply it to solve a maze. Now let's revisit our maze problem, and we will now use breadth first search to solve this problem. But before that, we need to model our maze properly. So the main idea is that we can represent this maze as a matrix with 0 indexed rows and columns, and we will mark open cells as 0 and blocked cells as 1. So basically a person can actually travel through the open cells, and this problem of finding a path in the maze now reduces to finding a path from the cell 0, 0 to 4, 5. Now we can use this matrix to build a graph where every two adjacent open cells are connected by a bidirectional edge if there is no block between them. Now here's what the resulting graph looks like. And when we simulate breadth first search algorithm on it, it works like this. We visit each node, and when we reach a particular node with multiple adjacent nodes, we discover them all at once. And then we move to the next child node in the queue. Now this is the most important characteristic of breadth first search. We process all nodes level by level. That is, we fully explore one level before moving on to the next. Now we will revisit this idea again later when we compare breadth first search with depth first search. And now let's shift gears and look at a completely different approach of graph traversal, the depth first search algorithm. Now depth first search algorithm is fundamentally different from breadth first search algorithm in the way it explores the graph. While BFS explores the graph level by level, depth first search tries to go as deep as possible along a path before backtracking. And if you see, the algorithm is similar to what we have seen for breadth first search, except that it's using a stack instead of a queue to keep track of the nodes. We will again represent the graph using an adjacency list as we did for breadth first search, which allows us to efficiently access all the neighboring nodes of any given vertex in a graph. Now, as with any traversal algorithm, we begin by marking all nodes as undiscovered. We then initialize a stack with the root node or the node we are starting depth first search from. Now inside the main loop, we first pop the top element of the stack, and if it's still undiscovered, we first mark it as discovered, and then we push all its adjacent nodes into the stack. And finally, the current node is marked as processed. Now, since DFS is inherently stack-based, we can actually write this traversal in a more elegant way using recursion. Now, if you're someone new to recursion and you find recursive solutions hard to grasp, don't worry, I will be covering recursion in detail in a separate video next week. But for now, to understand depth first search algorithm, we will be building up on the most fundamental assumption of recursion, that if we pass a vertex to this DFS module, it will correctly explore all its adjacent nodes. Note that this is also called a recursive leap strategy, and we will be discussing more about it in the separate video about recursion. Well, now the recursive version of depth first search is simple, intuitive, and easy to implement as well. In this recursive module, we first take a node, pass to this recursive function, we mark it as discovered, and then for each of its undiscovered adjacent nodes, we call the depth first search function again, and this continues until we reach a node that has no undiscovered nodes. Then the function starts returning back up the chain. Now this is called backtracking. Let's walk through a simulation using a recursive DFS tree to understand how it all fits together. Let's say we start with node 1. We mark it as discovered, and now we have an option to choose one of its adjacent nodes to recurse into. So let's say we recurse into node 2. We mark node 2 as discovered, And since it has no undiscovered adjacent nodes, we mark it as processed and then return back up the recursion stack. Back at node 1, we now have options to recurse into node 3 or node 4. Now let's now choose node 3. Again, we mark node 3 as discovered, and now we can go to either node 4 or node 5 from this particular node. Let's now recurse into node 5. We again mark it as discovered, and since it has no undiscovered neighbors, we can mark it as processed and return back. Now we recurse into node 4, mark it as discovered, and again, since all the neighbors are already visited, we mark it as processed and return back. Similarly, we mark node 3 as processed, and finally node 1 as well, completing our DFS traversal. Again, from an implementation point of view, it's helpful to know that we can actually track the discovery state of each node in a clean and simple way. Instead of using 3 separate labels for flagging undiscovered, discovered, and processed nodes, we can simplify this using a visited array, where each index in the array corresponds to a particular node. We again initialize all entries to false to indicate that the nodes are undiscovered, and when we first visit or discover a node, we set its value to true. Now, since DFS processes the node only after exploring all its neighbors in the recursive version, we don't need a separate processed marker as well. The call stack naturally handles that ordering. Well, with this understanding, we are now ready to apply depth-first search to search a maze as well. We will use the same graph that we have already seen during the breadth-first search simulation, and this time we will simulate it using depth-first search. And if we begin the depth-first search algorithm from the node 0, 0, what we observe is quite interesting. Depth-first search goes all the way up to the depth of the graph. It tries to find a path to the exit, and if it doesn't, it backtracks, explores another route, and continues this search until it finally finds a path to the exit 4, 5. Well, now that we have seen both depth-first search and breadth-first search in action, let's try to answer the most important question. What is the most fundamental difference between both of these algorithms? We'll try to answer this question using the same maze that we have seen before. Now we will take the graph representation of the maze we have seen earlier, and we will convert it into a tree representation. But what exactly is a tree? A tree is a graph without any cycles, where every child node of a particular node is placed in the next level. So if you observe, the first node is at level 1, the adjacent nodes for that particular node is at level 2, and we order all the nodes in a similar way. So over here, the height of the tree is basically the number of levels. In this case, we have 10 levels, and each adjacent node is placed at its respective depth. Now, if we simulate depth-first search on this tree, we will see that depth-first search goes all the way down one path to a certain depth, and if it doesn't find the exit, it will backtrack and then explore another path. Eventually, once it finds a valid path, depth-first search returns true or simply returns the path. Now, this highlights something important. If you notice, the depth-first search basically traverses all the way to the depth of the tree before it backtracks to continue the search on a different path. Now, this is one important difference we will see when we explore breadth-first search. Now, let's run breadth-first search on this graph to find out what is the most fundamental difference. Now, for BFS or breadth-first search, we again start off with the same node traversal sequence as we did for depth-first search, but now something interesting happens. If you observe, we are traversing the graph level by level, discovering all child nodes at a given level before moving to the next one. I'm going to pause this video and highlight this point. We are actually covering all the nodes at a particular level before covering the nodes in the next level. If you observe closely, all the nodes at level 6 are discovered before any of the nodes at level 7 are discovered. Now, this is the key characteristic of BFS. It fully explores one level before moving on to the next, as we discussed earlier as well. And this behavior of BFS actually allows it to find the shortest path in any unweighted graph as well. So the level at which a node is discovered using breadth-first search corresponds to the shortest distance from the starting node in terms of edges traversed. Let's now finish the simulation. We continue to traverse level by level, and finally, when we reach level 10, we find the target node or the path to the exit. Now, before moving ahead, let's discuss this thing in more detail. We mentioned that breadth first search can be used to find a shortest path in any unweighted graph. But if the graph doesn't have any cycles and it's unweighted, we can basically use depth first search as well, because in an unweighted graph with no cycles, there is only one path between any two vertices, and that's automatically the shortest path. But if we have a directed unweighted graphs without any cycles, things might get a bit messy. So it's better to use breadth first search for finding shortest path in any unweighted graph. Now I'm highlighting unweighted graphs since in weighted graphs, the shortest path might correspond to the sum of the edge widths, and for that we have a separate algorithm that we will discuss in the next few videos. Well, now that we know the most fundamental difference between both of these algorithms, let's try to compare them in a more detailed manner. Now, the time complexity for depth first search and breadth first search is big O of v plus e, where v is the number of vertices and e is the number of edges. Now, this is because we are visiting each vertex and edge exactly once during both the traversals. Now, let's talk about space complexity. For DFS, it's big O of v, and this space is used by the recursion stack or an explicit stack if we use the iterative version, and the visited array as well. For breadth first search, the space complexity is big O of v for the queue that stores the discovered nodes and the visited array as well. Now this is where things get interesting. The use cases. Depth first search is ideal if you want to explore a graph or you want to simply check if a path exists in a graph. Breadth first search, on the other hand, is useful for both of these cases and for also finding the shortest path to a node in an unweighted graph, thanks to its level by level traversal. And that sums up this video. I hope you have liked it. Do share it with your friends and do subscribe to my channel. I'd recommend that you visit trilab.io's notes and problem archives for code snippets around this traversal algorithms in C++ and other languages, and some more discussions around it. See you in the next videos. Take curious. Bye.